Okay, so for the next part is on green theorem. Okay, so when we talk about a green theorem, okay, so it's actually really a line integral over a simple closed curve in the plane. Okay, so the keyword here is a simple closed curve. Okay, so this is the keyword relate to Green's theorem. Okay, and also a double integral over the region bounded by the curve. Okay, so it's similar to what we learned in multiple integral, so specifically on double integration. Okay, so where do we apply Green's theorem? Okay, so under certain condition, okay, we can apply Green's theorem whenever we have a simple closed curve, okay, with a positive orientation. What it means by positive orientation, it should be in anti-clockwise direction. Okay, so if we have this condition, okay, we can evaluate that closed line integral, okay, on the xy plane, okay, using double integral like what we have learned previously. So it means that you are no longer need to solve the line integral using the method that we learned in this chapter, but you can use double integral. Okay, so you must recap back on whatever that you have learned on double integral. Okay, and then what it means by the simple closed curve. Okay, so the keyword here is it do not cross themselves. Okay, so simple would be like this. So this is what we say simple closed curve. Okay, for example, if we have like this, okay, so this one, okay, so we have a crossing over here, so this one is not considered simple. Okay, so the condition that we must follow, okay, whenever you would like to solve using Green theorem, okay, it must apply for simple closed curve and then positive orientation. However, for our scope, okay, it's gonna be we will ensure that whenever we ask the student to solve it using Green's theorem, okay, we'll ensure that the condition for the student to use Green theorem is satisfied first before we give that particular question. Okay, so by Green theorem, okay, is given by this one. Okay, so since we have a closed curve, right, so that's why we have this notation, okay, to represent the line integral. Okay, so this line integral, okay, for that specific region, okay, can be solved using this formula. Okay, so where f, okay, so where f, the vector field, is given by this one, f1 and f2 over here. So that's why we have this formula. Okay, and then please be informed that whenever when we learn on double integral previously, okay, it's covered by two coordinate, right, Cartesian and polar. Okay, so it's gonna be a similar practice as well. So whenever you have a circular type shape, okay, you can use polar coordinate because double integral, okay, involve for both, right, Cartesian and polar. Okay, so let's see example 10. Okay, so the question asks you to use Green theorem to evaluate this line integral, where C is the triangle with the vertices this point with positive orientation. Okay, so if we would like to sketch, okay, based on the given question, okay, so we have x and then we have y over here. Okay, so you are supposed to get a triangle like this, where this point is 1 0, okay, and then is 1 2, and then this point is 0 0, right? Okay, so the direction should be in this way, counterclockwise. Okay, so we know that this one is y equal to 0, okay, and then this one, okay, so it's gonna be y equal to 2x. Where this one coming from? Because of this point, right? Okay, so you're gonna get this one. Okay, it's gonna be like this because the what I'm supposed to say, the values of m for this particular general equation, right, mx plus c, right? So m should be the gradient, right? Okay, and then the c should be the intersection point on the y-axis, okay, coming out from this one. Okay, and then this line is represented by x equal to 1. It's important for us to know, right, because we would like to find the limit later. Okay, so this is the region. Okay, so this is the region that we would like to solve it. Okay, so based on the given question, so we know that f1 is equal to xy and f2 is equal to x squared y to the power of 3 over here. Okay, So for f1, okay, we're going to differentiate respect to y. So we're going to get x over here. And then for this one, we're going to differentiate respect to x over here. So it's going to be 2xy to the power of 3. Okay, so based on the formula, okay, based on the formula for this one, okay, so by right, we can write like this, right? So over here, it should be, okay, it should be f dot dr, like this, okay. So this one is going to be double integral, where this one is equal to 2xy to the power of 3 minus x over here, okay, and then dA. Okay, so since we have a triangle, okay, so it's supposed to be solved using Cartesian, right? So it's gonna be easy in that way to solve it. Okay, so for example, if I choose to solve using dy dx, okay, so the limit for x is between 0 up to 1, right? Okay, so it's gonna be 2xy to the power of 3 minus x. Okay, so dy dx over here, so it's gonna be 0 up to 1. Or the limit for y using vertical straight, okay, so it's gonna be from 0 up to 2x, from here up to here, right? Okay, so this is the limit. Okay, so up to this point, okay, you're gonna refresh back on whatever that you have learned so far using double integral. Okay, so if you solve this integral, okay, so you're gonna get that the final answer for this particular question is equal to 2 over 3. So that's how you solve, okay, that's how you solve the line integral, okay, that involve or that satisfied the condition for us to solve using Green theorem. Okay, so it is simple closed curve. Okay, so there is no crossing, right? So it should be a simple curve like this. Okay, and then is be based on the question, okay, it's supposed to be a positive orientation, so that's why we can solve it using Green's theorem. Okay, so you can try, okay, you can try to solve you for this example, okay, and then this exercise as well. So I did provide the final answer over here. Okay, so if we can take a look on example 11. Okay, so obviously that you're gonna have a region in circular type shape for this particular question, obviously. So the best way to solve this one is using polar instead of Cartesian. Okay, but no matter what, okay, whether you would like to solve it using Cartesian or polar, it's up to you. Okay, just make sure that the integral that you got, okay, when you move to this side, okay, is it's a simple to solve the integral. Okay, if it seems complicated, means that you might have to change the coordinate. That's all for this video. Thank you.